So let's talk about integration. So what is integration? Well, most people would tell you it's the opposite of differentiation. And some notation first. So this is how you write the integral. It's like an S, it's like a curly long S, and then you have the function in here, whatever that is. And then you have the dx again. So that means with respect to x. And then you get a value over here. And depending on the function, you get different values on the right hand side right here. So this is just right hand side. So, what is integration useful for? So remember, if you have a curve, once again, with lines everything is easy, but when it comes to curves, we need some more tools. So let's say we had a curve that looked like that, right? Something like that. Now we know how to find the gradient at any point. We can draw a tangent. We can find the gradient at any point we want. But let's forget about the gradient. Let's say we wanted to find, for some reason, the area underneath the curve. So let's say we wanted to find the area between this and this point. So let's say that point is A and that point is B. Let's say we wanted to find the area of this region right here inside. How would we do that? Well, one thing that we can do is let's say we can make like rectangles, right? Let's say we had a rectangle that looked like that, and then another rectangle that looked like that, and then another one that looks something like this. And then you can like approximate with rectangles. You can make them as short as you want, as long as you want. Let's say those were our rectangles, right? That would get us pretty close to the area. Like, we would almost get the exact area, but of course it won't be precise because, rectangles are basically straight lines and we have a curve. So it's impossible to just get it by only doing rectangles. But what if we kept on making like the width extremely small? So like it was very, very small, and then we drew the line again. And then again, very, very small, and then do another rectangle. So now you can see we would have many rectangles, and they would give us a better approximation of the area underneath this curve right here between the region between A and B. And there's like a formal way to get the proof and everything, but I'll just tell you. So let's say this curve was y is equal to x squared plus 2x, right? The way you would get the area underneath the curve is you would integrate, so that's the integral sign, and then you have the function right here. So you have the curve x squared plus 2x, and then you have dx, of course, right? So this is one thing and dx is the other thing. This just means with respect to x. This comes in very useful later on. And you want to do it between a and b. So b is your upper bound and a is your lower bound. So what this is telling you is that when you actually calculate this, you'll get the area of the curve between a and b, and the curve is x squared plus 2x, and this will be the exact area. And the way you do it is, so you have to find a function that when you differentiate gives you y. So now you have y, right? If you differentiated this, you would get 2x plus 2. But now I want something else that when I differentiate that, I get x squared plus 2x. So it's like y is the derivative already. So we need to find the integral of y. Well, how do you do that? For the derivative, from the power rule, remember, we bring the power down, multiply by the thing, and then reduce the power by 1, right? Well, for the integral, we go in reverse. So now we have the power 2 right here. So we bring the power up by 1, 3, and then we divide by the power, which is 3. And we can do it for 2x. So that's 2x to the power 1. So now what we do is, so we have plus 2, and then x, we raise the power by 1, so it becomes 2. And then we divide by the new power, so divided by 2. So that is the integral. So the integral of this is actually x cubed over 3 plus x squared. And you can see if you differentiate this with respect to x, you would end up getting 3x squared divided by 3, which is x squared, plus 2x, which is what we need. So that's the integral. And then this is between a and b. So what we do is we make like big square brackets, and then we put b on top here and a on the bottom here. And that just means that whatever the number for b is, so let's say b was 5, and let's say a was 3. Then we would put the number 5 into this first, so we would have 5 cubed over 3 plus 5 squared. And then you would subtract whatever is in here when you put a back into it. So you would have, let's say a is 3, so we have 3 cubed over 3 plus 3 squared. And that would be your final answer. That would be your answer for the area underneath the curve between a and b for the curve y is equal to x squared plus 2x. Now, let's say you didn't want to find the area. Let's say you wanted to find the area, but like it wasn't between any bounds. Let's say you just wanted to integrate. So remember, when you differentiate something, when you differentiate just a number, so a constant like 6, you get 0. When you differentiate another constant, let's say negative 35, remember, this is x to the power 0, this is x to the power 0. And you know what happens, right? It's like you do 0 times negative 35 times x to the power minus 1, which is still 0. So differentiating any number by itself, which just gives you 0. So when you integrate, you need to make sure that you add the integrating constant, which is a c. So make sure you always add a plus c, and this c can literally be any number. It could be 6, it could be negative 35, it could be anything. So if I tell you to calculate the integral of, so if I tell you to just do this, integral of 2x cubed plus x with respect to x, and I don't give you any numbers, I don't give you b and a, I just tell you to do this. The way you would do this is, you would do the exact same thing. So you would have the 2 in front, and then x to the power, 3 plus 1 is 4, divided by 4, plus, and then x to the power 1 plus 1 is 2, and then divided by 2. And then you would just add a plus c. That's it, that's all you have to do. Literally, just make sure you add the plus c, because when you differentiate this, you would get this back, but then you also have to differentiate something right here. And the c could be 0, but we always make sure we include it in there. So let's see why this actually works. Let's do an example of, let's do something that we can work with easily. Let's do a triangle, because we know how to calculate the area of a triangle. So let's say we had y is equal to x, right? Let's say that's our line, y is equal to x. Let's say that's 5, and that's 5. Right? Because y is equal to x, they would be matching. So this would be like 3, and that would also be like 3, right here. Let's say we want to calculate the area of this smaller triangle right here. So between 3 and 0. Well, how do we do that? We do base times height divided by 2. So we do 3 times 3, 9 divided by 2, which is 4.5. So that's our area. So we know this already. Can we do it by integration? So integration should give us the area, right? Well, we have y is equal to x. So I'm claiming that if you integrate the function, so if you integrate x with respect to x, between the numbers 0 and 3, because you're going from 0 to 3, you should get 4.5. Well, let's do it. So the integral of x is just x to the power 1 plus 1 is 2 divided by 2. And we don't need the plus c this time because we have actual numbers. So now we just do 3 and 0. So now we evaluate at 3 and 0. Well, what's 3 squared divided by 2? That's 4.5. Minus, what's 0 squared divided by 2? That's just 0. So we get 4.5. So that worked. What if we did between 3 and 5? Well, now it's not that easy because now we have a trapezium, right? So that's going to be difficult for us to do by hand. But now, instead of 3 and 0 right here, what if I just did x squared over 2? If I just did 5 and 3? Now this becomes faster than doing it by hand, like how we're used to doing it, because it's way more difficult to calculate the area for trapezium than just putting numbers into this right here. So you would have 25 over 2 minus 9 over 2. And that would give us 16 over 2, which is just 8. Look at how quick that was. So the area right here is 8. The area right here is 4.5. And does it make sense? Let's think about it. So that means the total area of this triangle is 12.5, right? Because 8 plus 4.5 gives you 12.5. But this whole thing right here is also a triangle. It's a triangle with length, with base 5 and height 5. And what's the area of a triangle with base and height 5? That would just be 5 times 5 divided by 2, which is also 12.5. So you can see this integrating thing is actually real. Like, it does work. And sometimes when a function is way more complicated, like this right here, or something that looks even more insane. Let's say we had something that looks like this. Let's say that's our function, right? And I want to find the area between here and here. How can I do that? There's no way for me to like do it with the rectangles. And that's when you would use integration. You would have the function given to you, you would integrate it, and you'd find the area between the 2 points, let's say C and D. So let's do like an example question. And perhaps it will make more sense. Well, honestly, with integration, you just have to practice enough and you'll get used to it eventually. So the diagram shows the curve of the equation y is equal to square root of x plus 4x to the power negative a half. The line y is equal to 5, so this is 5 right here, so write that down, intersects the curve at the points A 1, 5, so that's 1, and B 16, 5, so that's 16. Okay, so far we're good. Find the equation of the tangent to the curve at the point. Okay, so this is differentiation actually, because tangent means we need to find the equation of a line that looks something like this. So a line looks something like that. Well, let's see how we can get the equation of the tangent. So we know when you see tangent and curve, differentiation should go to your mind straight away. So dy by dx is equal to, well, power rule, so that would be a half times x to the power half minus 1 is negative a half, plus 4 times, well, now you have negative a half, times x to the power negative 3 over 2. Let's write it better, so that becomes 1 over 2 square root x minus 2 over x to the power 3 over 2. And we need the equation of the tangent at the point A. So A, the x coordinate is 1. So if you put 1 into here, we should get the gradient at that point. So we would have 1 divided by 2 square root of 1 is just 2, minus 2 divided by 1 to the power 3 over 2 is just 1. So that's that. So a half minus 2 is negative 3 halves. So we've made progress so far. So we have the equation y is equal to negative 3 over 2 times x plus c, because y is equal to mx plus c, and we already know m is negative 3 over 2. So how can we get c? Well, it's pretty simple, right? We know one of the point it goes through. We don't know this point, we don't know anything else, but we know it goes through the point 1 and 5. So when y is equal to 5, x is equal to 1. So 3 times negative 3 over 2 times 1 is just negative 3 over 2, and then plus c. Well, you can rearrange this to get c is equal to 5 plus 3 over 2. Well, that's just 13 over 2. And that's it. You have the equation of the tangent at that point is y is equal to negative 3x over 2 plus 13 over 2. So now we saw how differentiation can be useful for this curve. We can find the equation of the tangent at that particular point. Now let's look at the next thing. Calculate the area of the shaded region. So now we want to calculate the area of just this thing right here. So far with integration we learned that, let's say I had this right here. If I integrated this curve, I'd be able, so if I integrate this curve right here, so there's two different things. There's y is equal to 5 is a straight line, and then y is equal to square root of x plus 4x to the negative a half is this curve. And if I integrate the curve between 16 and 1, I should get all of this area right here. This thing, this thing, this thing, all of this area. But we don't want that area. We only want the area from here. So there's two ways to do it. So you can see this is a rectangle, right? This is just a rectangle of length 15 and height 5. So if I did 15 times 5, that's 75. That's the area of the whole rectangle, everything included. And if I subtract the area of the curve, the area underneath the curve from 75, then I'll be left with this area right here, which is the area that we need. So we can just do 75 minus area underneath the curve. Well, let's do that. And instead of getting 75 from there, we could just have y is equal to 5 as one of the other curves. So we could instead, well, let's do it both ways actually. Let's do the first way I said first so we don't get confused. So to calculate the area, we're going to do the integral of the function is x to the half plus 4x to the negative a half. So x to the half plus 4x to the negative a half with respect to x. And we're going to go from 16 to 1. Is that, I think those are the bounds. Yeah, 16 and 1. People say we're going to go from 1 to 16. Same thing. 16 to 1, 1 to 16. Just make sure you write it in the right order. So what will we get? So we use the reverse power rule. So we have a half. So we add 1 now. So we have x to the power 3 over 2. And we divide by 3 over 2. Well, dividing by a fraction means multiplying by the reciprocal. So that becomes 2 over 3. Plus 4x. And then we add 1 again, so it becomes positive a half. And then dividing by a half is like multiplying by 2, so that's times 2. And then, of course, between 16 and 1. Well, that's pretty simple. Now we have 2x to the power 3 over 2 over 3 plus 8 square root x between 16 and 1. And it's convenient that 16 is a squared number. So now we have 16 to the power 3 over 2 is just 4 to the power 3, which is 64. 64 times 2 is 128. So we have 128 over 3. Plus 8 times square root of 16 is 8 times 4, which is 32. So we have that. Minus, well, put 1 back in here. We have 1 to the power 3 over 2 times 2 over 3 is just 2 over 3. Plus 8 times the square root of 1 is just 8. So we have that. What can we do now? Well, we can just subtract. So we have 128 minus 2 over 3 is 126 over 3. That can be simplified. That is actually just 42. That's right, 42 on top, so I remember. Plus 32 minus 8 is just 24. So we have 42 plus 24, which is equal to 66. So that's the area underneath the curve. So that is this area right here. This whole thing is 66. Which makes sense that it's less than 75, right? Because this rectangle is 75. So now we want the area of just this thing right here. Well, if we did 75 minus 66, then we get that answer, right? Because just subtracting the areas. 75 minus 66, which is just 9. So that area right there, which there's no way you could calculate this without knowing integration, or at least so far, you'd get 9. You wouldn't be able to get 9 as your answer. Like, there's no way you can approximate that perfectly. And by integration, you can see that 9 units squared, centimeters, meters, whatever. But 9 square units is the final answer for that. And now what I was saying earlier is that you could do the difference between two curves. So y is equal to 5 is actually a curve as well. So y is equal to 5 is another curve. And y is equal to 4x to the half, or is it x to the half plus 4x to the negative a half? Plus 4x to the negative a half. That's the other curve, right? Yeah, x to the half plus 4x to the negative a half. So if I want to find the area and that's the difference, well, let's call this y1, let's call this y2. I can just do the integral of y1 minus y2 with respect to x between 16 and 1. And let's see if that gives us the same answer. So we would have the integral of 5 minus x to the half minus 4x to the negative a half with respect to x between 16 and 1. And you shouldn't be surprised when we get the same answer, because of course we'll get the same answer. So we get the integral of 5 is just 5 times x. Because this is 5x to the power 0 basically. So when you integrate this, you get 0 plus 1 is 1. So you have 5x to the 1 divided by 1, which is just 5. So 5x to the 1, which is 5x, minus x to the power 3 over 2 divided by 3 over 2 becomes 2 over 3, minus 4x to the half dividing by a half is times 2. And then this is all between 16 and 1. So let's see what happens now. So now we have 5x minus 2x to the power 3 over 2 divided by 3 minus 8 square root x, all between 16 and 1. So if you put 16 in, you get 16 times 5 is 80, minus 16 to the power 3 over 2 is 64 times 2 is 128, divided by 3 is 128 over 3, and then minus 32, because square root of 16 is 4, 4 times 8 is 32, and then minus 5 times 1 is 5, minus 2 over 3 minus 8. So let's see if you get the same thing. Well, you'd get, let's do it right here. You get 80 minus 32 is 48, sorry. So you have 48 minus 128 over 3. And then you're subtracting. 5 minus 8 is negative 3. So you have negative 3 minus 2 over 3. So that is equal to, well, we do 48 minus 3, so that's 51. That's nice to work with. And then you have minus 128 over 3 minus 2 over 3, so that's 130 over 3. So now we have minus 128 plus 2 over 3. Oh, sorry, that's minus 126 over 3. I don't know what I'm saying. Because you think minus 128 over 3 plus 2 over 3, so that's minus 126 over 3. And minus 126 over 3 is just minus 42. So now we have 51 minus 42, which is equal to 9. And that is what we got at the start here as well. We got 9 units squared. And in this case, it was easy to recognize that it was a rectangle. So we could calculate the area of the rectangle however we know how to do it. So just base times height, and then subtract the area of the curve from there. But let's say you wanted to find the area between two curves, right? Let's say you wanted to find the area of something like this, and then a curve that looked like this. Let's say you wanted to find that area right there. How would you find that? Well, you see this curve right here, we can integrate that. So you get the whole area right here, so this whole thing. And then you can subtract by the integral of this small curve right here that's underneath it. And that way you can get the area that you need. So you can see you can integrate between, so now you can't just, you can also find the area between two curves at this point. So let's say you wanted to find this area right here, that would just be an integral. But now this area right here is an area between two curves, because y is equal to 5 is technically a curve as well. It's a curve that's a straight line. So whatever you want to call it, but it's still a curve. So now you can see how important integration is and how useful it can be. So yeah, I hope you liked that video. It's a bit on the longer side. And with integration, you just have to practice a lot, and eventually you will see that it's not that bad at all. So, and we'll cover some more integration techniques for more complex functions in other videos. So yeah, like, comment, subscribe, and let me know what else you want to see in the future videos.